Good morning, all of you. Welcome to the expert lecture on some application of logic in discrete mathematics. I, Dr. Rinku Verma, take this opportunity to welcome our dignitaries, our Honorable Vice Chancellor, Dr. Sunil K. Somani. Sir, it is a great privilege for us to have you with us today. Our hearty welcome to our expert, Dr. Kamala Krithivasan, Professor IIT Madras. It is an honor and privilege for us, Madam, to have you with us today. I also welcome our Dean Science, Dr. Preeti Jain, HOD Mathematics, Dr. Rekha Jain, all HODs, all faculty members, and dear students. I'm sure that today's lecture inspires us and build our knowledge on application of logic in discrete mathematics, which is very helpful for us and our students. Now I would like to invite Ms. Megha Srivastav for introducing our expert, Dr. Kamala Krithivasan. Ms. Megha, please.
Thank you, ma'am. Good morning to all. I, Megha Srivastav, take a pleasure to discuss the profile of our eminent speaker, Dr. Kamala Krithivasan, who has served as faculty member of the Computer Science and Engineering Department, IIT Madras, Chennai in 1975. She obtained her bachelor's and master's degree in mathematics from Madras Christian College, Tambaram, affiliated to Madras University, where she was first rank holder. She also received her PhD from the same Madras University in array grammars. She joined IIT in 1975 and became professor in 1990. She held the post of chairperson of the department. She has been associated with researches in the field of theoretical computer science. She has also done work in computational geometry. She has taught courses on and related to discrete mathematics and theory of computing numerous times. She has also delivered many lectures on discrete mathematical structures and some on theory of computing under the NPTEL program. She has guided many PhD and MS students and handled many projects. She was awarded Fulbright Fellowship in 1986. She visited University of Maryland during the fellowship period and afterwards Concordia University for 6 months. She has visited many other countries for presenting research papers. She was elected as a Fellow of Indian Academy of Engineers in 2006. At present, she is a member of the Governing Council of INEAE. She was awarded Lifetime Achievement Award by ISTE in 2019. She has authored Introduction to Automata Theory, Formal Language and Computation, published by Pearson Education. She has also authored Indian Adaptation of Discrete Mathematics and its Application with Combinatorics and Graph Theory by Kenneth H. Rosen. This semester, she is teaching an online course on logic and combinatorics in CS for UOP program at IIT Madras. Now, I would like to invite Dr. Kamala Krithivasan to share her knowledge with us. Please, ma'am.
Thank you. Thank you, Rinku Verma and others for the invitation. It's a pleasure to talk to the students on applications of discrete mathematics and logic. Usually, the question arises. I think the audience mainly consists of IT students and CS students. So when you take BTech IT or CS, and you are asked to take a course on discrete mathematics or theory of computation in the second year or so, the question many students feel is, why should I learn this course? what is the advantage? Afterwards, I'm going to work with Amazon, I'm going to work with Google or something like that, or an IT company. What is benefit will I get from learning discrete mathematics? And let me tell you, it is very, very essential because discrete mathematics lays the foundations for many of the other courses. If you learn this course, understand this course very well, then it will be easy to tackle problems in the other courses. Because you see, you are going to build a construction, and when you build a construction, the foundation has to be very strong. If you have the foundation very strong, and then the upper structure, even after some time, it collapses, the foundation is strong, you can build again over the foundation. But if the foundation is not strong, then the whole building will collapse in a few years. That is what you must understand. And this is a very, very basic course which will be used in many of the other courses. Sometimes you outwardly you will realize, sometimes you may not even realize that you are using discrete mathematics. Like, when I joined IIT Madras in 1975, we never had PC. PC was not there. Nothing was there. I mean, a very big computer occupying a very big hall, IBM 370-155 was there. And the languages, programming languages taught were Fortran, PL1 and COBOL. So at that time, the students used to think that computer science means mainly learning Fortran, PL1 and COBOL. Why should we learn other things in the subject, in the course? Now, if they have learned just Fortran or PL1 or COBOL, what progress will they make now? See, the scenario keeps on changing. You can very easily see that now the C++, JavaScript, Java, Python, these are the languages. So one has to keep on updating. Even like now we are having an online Zoom meeting, and you are able to hear me from, I am sitting in my home. So things have changed so much, and it keeps on changing. So we have to adapt ourselves to the changes, and to adapt to changes, we should have the basic foundation laid very strongly. That is what is given in discrete mathematics. Now let me also tell you something. You will be also asked to take some courses in mathematics on integrals, partial differential equation, probability and so on. Why should you learn that all? Because later on somewhere you will be using them. So some basics of mathematics is very essential, some is necessary. Similarly, it is also very necessary to learn discrete mathematics. And when you are dealing with a subject like calculus, what will be initially taught? Initially differential, you are starting with differential equations, then derivatives, differentiation. Then you will be taught d by dx of x squared is 2x, d by dx of x power n is n x power n minus 1 and all. Immediately they will not tell you that where it is going to be used. But after some time you will learn that the velocity of a system is given by ds by dt. The acceleration is given by dv by dt. If you want to study planetary motion or the velocity of any particle or anything like that, you should know differentiation. And it is not just some function. The function on which you want to differentiate may be a very complicated function. So you have to understand how to differentiate the product UV. Differential of UV will be UDV plus VDU. Like that, people will teach you. When they teach you, they will not immediately talk about the application. It will come later. Similarly, when you study in discrete mathematics about sets, relations, functions, and all that, the application they may mention, but it will come later. So you should be very ready to learn the mathematics, and don't ever think that whatever you are learning is not important or something like that. Recently, you might have heard that the Nobel Prize for Physics has been awarded to 3 people for their study on black holes. And 50% of the award goes to Roger Penrose, who did some very effective work on black holes. His work only laid the foundation that black holes can exist. And his work was mainly mathematical. Earlier, people thought that something like, when the stars are they are starting to die, the whole gravitational force of them will be increased so much that anything goes near them will be attracted and eaten by them. But see, what Roger Penrose, he didn't consider it as very. Initially, people thought of spherical things only. So he didn't think of spherical. He used topology and what is known as conformal mapping, and any surface, how it can become a black hole. That is what what was done in about 1960. And later on, recently, people have realized that, at the time itself, he said it's not only theoretical work, it practically also black holes can exist in nature. And later, many other people worked on that, and now they have shown that black holes do exist. And all this, the initial initiative was by a person who was working on mathematics. Okay? So many of the results are very important from mathematical point of view. And today I thought of talking about 2 major breakthrough results in theoretical computer science or mathematics in the first half of 20th century. One is the concept of undecidability, and the other one is Gödel's incompleteness theorem. These 2 are mainly based on logic and also on Turing machine theory of computation. If you come across, it will be on Turing machines. A.M. Turing was the person who talked about the halting problem. And Gödel's incompleteness theorem also shows some basic inherent deficiency in integer mathematics. So I will just talk about them and also briefly mention about other applications of, if time permits, about other applications of, okay. Rather, I will say a few words about the other applications of discrete mathematics before going into the technical part. See, graph theory is very, very useful because the whole network is based on net. You have computer networks, every system is connected to another system, and that is underlying structure is a graph. And there are so many routing algorithms, how the packets are sent from a source to a destination. So the underlying, you have to learn about the underlying structure and also the cost involved in sending some packets through a link. And what is the minimum weighted path so that you can send the packets through that. And you should also make sure that the packets, the traffic is not overloaded. If the traffic is overloaded, you have to send route to another. So many work has been done, is still being done on routing, how the suddenly one of the link may become faulty. You may not be able to send the link. Already if you are sending, some of the packets may be lost. So you have to find another route. Immediately you have to understand that and restructure the routing algorithm so that it is sent through the other thing. So for all this, lot of graph theory is necessary. And also you have to decide by which route you have to send the packets. And the decision algorithm, how you are going to send, that decision has to be done very quickly. So the question of what algorithm you are going to use and the complexity of that algorithm becomes important. So you talk about the complexity of an algorithm. And it can be, I don't know whether you have been taught about the big O notation. Anyway, I will not go into the details. If you have an order n cubed algorithm, that is slower than an order n squared algorithm. And if you have a 2 power n algorithm, that is much slower than order n cubed algorithm. So the growth of functions become necessary. You have to study about the growth of functions. And what is the growth of functions? You have to study about functions first to study about the growth of functions. So functions, it becomes necessary to study about functions. And if you have relational database systems, lot of relations are used, and then you have the SQL language and the relational algebra, relational calculus, tuple relational calculus, and so on, domain relational calculus. All this use a lot of concept about relations and also logic. You have n-array relations. What is the projection operation? What is the selection operation? What is the join operation? All this you are taught in relations so that they are used in relational database systems and the SQL. So that way, relations are important, functions are important, sets are important, graph theory is important, everything is important. So you see, it is very essential to understand that the basics. Even though if you take up a job in say an IT company, now I'm going to tell why it is necessary to study undecidability and also the NP completeness. Anyway, I will not be dealing with NP completeness. NP completeness is really, an algorithm is, okay, I will start with undecidability first. Suppose you are working in a company, an IT company, your boss calls you and he gives you a problem. This is the problem specification. Come out with a good algorithm tomorrow. And you go home. You try. You are not able to do the next day. You are not able to come out with the algorithm. Then the next day also you spend and still you are not able to get an algorithm. So if you go and tell your boss, I'm sorry, I'm not able to get an algorithm for the problem you have specified, he will get very angry. He may even fire you. But if you, instead of telling that I am not able to find an algorithm, if we can prove that nobody can ever find an algorithm for the problem specified, it will be wonderful. He will realize that the problem he has given is not one for which you can find an algorithm, right? Then he will have a very good impression about you and maybe changing the problem a little, somewhat, or restricting the problem so that you are able to write it. So people in the, as I told you, the first half of 20th century, 1901, Hilbert, a person called Hilbert, he gave many problems, and one is called Hilbert's 10th problem. The Hilbert's 10th problem is, given an integral equation with integer coefficients, are the roots integral? are the roots integers. Supposing you take a quadratic equation, it is difficult to switch back to writing and talking. So I am not writing it on the thing now. Afterwards I will start writing on the iPad. So I'm just mentioning this a small equation. Suppose you are having a equation x squared plus 3x plus 2 is equal to 0. You know that it is having integer roots, minus 1 and minus 2, right? This is a single instance. Please note that it's a single instance of a problem. If you have x squared plus x plus 1 is equal to 0, this will not have integral roots or real root. So you know that for small cases you may be able to find. Suppose I have a polynomial with integral coefficient degree and 100, so it will have 100 roots. Are all the roots integers or not? Because if you have a particular equation, you may try to factorize and find out. It is going to take a lot of time, but still you may be able to find it. But in general, the input is some equation of a high order polynomial equal to 0. And the question is, are the roots integers or not? Can you write a general algorithm which can do that without actually factorizing? You can say factorize and find out, no, that is not true. In general, can you given an equation, can you generally say by some method, design an algorithm which will tell whether the equation will have integer coefficients in integer roots or not? The polynomial has integer coefficients and are the roots integers. People tried for so many years, 35, 36 years people tried on that. Then in 1936, A.M. Turing came out with the concept of undecidability. And he said that there are problems for which nobody can ever write an algorithm. Please remember that it is not that you don't know how to write an algorithm, or I don't know how to write an algorithm, or after some working you may be able to find an algorithm and so on. It is the statement that for such a problem, nobody can ever write an algorithm. And it is very difficult to prove that. Please remember that it's not very easy. It is very difficult to prove such a statement. And that is a major break. And once he stated that, people realized that the Hilbert strength problem is one such problem. Nobody can ever write an algorithm. Then people stop trying that. That's what I said. When your boss asks you to do a problem, you are not able to come out with an algorithm, but you are able to prove that nobody can ever write an algorithm. That is a very important step. And that is what is done in the unsolvability concept. So I'll briefly explain that concept in the coming few minutes. Another one is NP completeness. This I'm not going to talk about that. If you have a polynomial time algorithm for a problem, it is efficient. If you are having only exponential time algorithm, it is not considered efficient, because as the size of the problem grows, the time it's going to take is enormous. So you are not interested in having exponential time algorithm. So again, I'll come to the same problem. You are working in a firm and your boss gives you some problem, and he says try to come out with a very good algorithm for this. You go home, you try to write an algorithm. You are able to write an algorithm, but when you try to find the time complexity of the algorithm, it is taking exponential time. You will just change the algorithm, but still you are not able to get a polynomial time algorithm. So that is not a very efficient algorithm. If you go and tell your boss, sir, I have given an algorithm, but it is not a polynomial time, it is taking exponential time. He is going to get angry because practically it cannot be used. As the size of the problem is going to increase, it will take days, months to work on the problem, and then it will be of no use. So he is going to get angry. But instead, if you tell him that, see, the problem is such that it is an NP complete problem. If you can find a polynomial time algorithm for this, so many other problems are there listed as NP complete problem. They will also have polynomial time. That is not possible. In a way, it is saying that I am not able to come out with the polynomial time algorithm. Neither X, neither Y, neither Z, they also cannot come out with that. It's something like that with a polynomial time algorithm. Then the boss will be happy. Oh, yes. Please note that it's just not saying, you have to prove it. So if you have to prove that a problem is undesirable, you have to prove it. If you say it's NP complete, you have to prove it. Okay? All those techniques are taught in discrete mathematics. There is a section on proof techniques, different types of proof techniques which are used in your everyday life, in everyday mathematics, and how that is important, and so on. So having said that, I shall go to the decidability result first. Then we'll see how much time it takes, and then go on to borders and incompleteness theorem. Now I'll switch on to the writing section, board section. So you'll not be able to see me, but you'll be able to see the board. Are you able to see that? Are you able to see?
Yes, ma'am.
Yes, ma'am.
So first I'll talk about decidability. This is to say that there are problems for which nobody can ever write an algorithm. Please note that it is a very strong statement. It's a very strong statement because it's not that, as I told you, you can write, cannot write, I am not able to write, you are not able to write, like that. Nobody can ever write an algorithm. Now for this was mainly considered by A.M. Turing. He defined what is called a Turing machine, 1936. He defined something called a Turing machine. If you have studying theory of computation, you will study this. And with respect to that, he showed what is meant by an halting problem. Now I am not going to do Turing machine ourselves. I am going to discuss this in a slightly different way. Now you are writing computer program, and I am not using any particular language. Pseudo code only I am going to write. Suppose you have a program. Begin. X is equal to 2, y is equal to 3, z. So this program will take x and y as 2 and 3. You can also have read x and y and give 2 and 3 as input. Z will be 2 plus 5. This will print an answer 5. This is a program which will halt. This program will halt. This will. Anyway, in practice, we keep a restriction on the time spent. After some time, the program will automatically say that the timed out or something like that. Or the memory also, if you use too much of memory overflow will be there. And it says that this program cannot be done because the memory is not enough or something like that. So there is a restriction on memory and there is a restriction on time for any program to run. But suppose I am thinking of a computer where there is no restriction on time. You can run it for any amount of time you want. And there is no restriction on memory. Any amount of memory you can use. If the memory is not enough, you can keep on adding. And we are not putting any restriction on time and space, time and memory. In that case, can you find out whether, see, let me also write a program. Begin. I is equal to 1, while true. Begin. So what will this program do? It will print 1, then it will print 2, it will print 3, it will print 4, it will print 5, and keep on printing. As we have not put any restriction on time and memory, this will keep on running. It is not going to stop. So this is a program because a program tells you what to do at the next step. Okay, this program will not sometimes whether it will halt or not depends on the input. Sometimes whether a program will halt or not depends suppose I write a program to calculate factorial n. So I said read n, that is equal to n. while n, or repeat until you can use. N greater than. So this portion will execute again and again. So initially it will be n, then n minus 1, then n minus 2, till you get 1. So you are calculating factorial n like this. If you are not checking if n is greater than or not checking. This portion, if n is less than 0, it is say minus 5. It will keep on multiply by minus 5, minus 6, minus 7, like that. So this, it will not stop. If you are not adding a checking statement, like if n is only when n is greater than 0, you execute the program. So it will calculate factorial n if n is greater than 0, but it will not halt if n is less than 0. So whether a program will halt or not will depend on the input. Whether a program will halt or not depend on input. Will or can depend on it. So let us consider only input free programs. Let us consider only input free program. So if you want to give an input, you can give as an assignment statement. So begin, and then if you want read, instead of read n, you can say x is equal to n, something, whatever, n is equal to something, or x is equal to something, you can give by whatever read and stuff. Read, you can give as assignment statement. Now, under this, you are considering only input free programs. Can you write a program? Can you write a program halt which will take as input an input free program P and tell whether we will, that is, you are able to write a program halt. The input to the program is any input. If you are able to write a program, the halt, for halt, the input is a input pre-program, and it will say yes, P halts, or it will say no, P does not. Now you want to prove that you cannot write a program like, want to show that you cannot write a program like halt. Here you use a method called proof by contradiction. Proof by contradiction, which is also called reductio ad absurdum. So what in this, you assume that suppose a program like halts, halt, a program halt exists. Then you show that you are arriving at a contradiction, right? Then you write a program absurd. I want to show that this leads to a contradiction. Absurd, it tells you that begin if halt of absurd is equal to yes, then begin while print and else stop. And this begin has an end. You are writing a program like this. If halt of absurd is the program, it is halt of absurd is yes, then begin while true print haha, end, else stop. Now does absurd halt question. It is an please note that it's an input pre-program. So absurd, there are two possibilities. It halts. Another thing is it does not halt. If it halts, what happens? The answer is yes. If absurd halts, the answer is yes. Then the then portion of the program will be executed. This portion says you keep on printing ha 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 ha. System laughs at you. Okay? So it keeps on printing ha 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 ha, and the system laughs at you. And what it says is, then you come to the conclusion, is that's not halt. It keeps on printing ha ha. If you assume it does not halt, then the answer is no. So the else portion will be executed. So it halts. So in essence, if you assume that it halts, you come to the conclusion it does not halt. If you assume it does not halt, you come to the conclusion it halts. That means there is a contradiction, and the contradiction has come because you are assuming that you can write a program like halt. So the contradiction the contradiction has come because you assumed a program like hard can exist. Therefore, a program like hard cannot exist. So, here you are proving that you cannot write a program like hard. It is, again, I am emphasizing, it is not that you don't know how to write or I don't know how to write. Nobody can ever write a program like hard. So it's a very strong statement, and that is the concept of undecidability. There's a technique how you can prove new problems to be undecidable. You have to reduce that. You have to know, reduce a known undecidable problem to that, and so on. That is a very, I mean, lengthy theory of computation you will study, but not in discrete mathematics. Anyway, this is to tell you that why it is important to learn. You have something you are not able to write an algorithm. You have to show that nobody can ever write an algorithm. And if you are not able to write an efficient algorithm, you have to say that it is an NP-complete problem. There is nobody can also, I mean, there are so many other algorithms which will become efficient if you are able to write an efficient algorithm for that. So this is about, as I told you, 3 results I really, the proof I really appreciate. One, the major results. One is Gödel's in this undecidability, and another is Gödel's in incompleteness theorem. And the second argument is Cook's theorem, showing that Boolean satisfiability is NP-complete. The proof is very beautiful. You see the proof, the beauty of it is so attractive that you will enjoy that. It's a very lengthy proof, but still students like it. I mean, the proof is very attractive. Okay, anyway, I don't have that much time. How much more time do I have?
Ma'am, you can take 5 minutes more.
5 minutes?
Yeah, ma'am.
Then I will not have time for Gödel's incompleteness theorem.
Yes, ma'am. You can conclude this lecture.
Okay. Okay. So, another thing which is, as I told you, is that if you have integer arithmetic, that is Gödel's incompleteness arithmetic, then for rules of rules and axioms, then you will see that there are 2 statements which cannot be proved. This is or in an this is the defect is inherent in the system itself. Again, I cannot explain it in 5 minutes. We'll leave it. So I'll go back to read. So we have, so this, as I told you, this is just to tell you how important it is. Now the last 5 minutes, I will sort of tell you other importance. You may think that this old lady is giving a lot of advice, and you may think it is, but anyway, I will spend giving some advice. So it's a young, you are all young, and you should not take anything without seriousness. With all seriousness, you do your studies, and also don't ever think something is unimportant. Everything is important. Later on, you'll find a use for that. And the thing is, what should I say? You have to keep on practicing, keep on learning, keep on updating yourself, because as I told you, when I joined IIT, there were only Fortran and PL1 was there. Now so many languages are there. One has to update the knowledge, keep on updating the knowledge by learning new things. And also anything what you learn will be of helpful. And younger age, you have to make full use of your time, learn as many things as possible. In fact, you would have found that if you have seen Goddess Saraswati's statue, she will be holding a veena and she will be playing on the veena with two hands. One hand she will be using Jabamala, and another hand there will be some, I don't know what is the correct word. It's called Olai Chugudi in Tamil. You will have where something will be written on that, like books, you'll be having some book on that. She is the goddess of learning. Even though she is the goddess of learning, she keeps on practicing Veena, reading more and more. There is no end to learning. You can learn even when you become very old. You can learn. There is an end to the life, but not end to learning. Even Goddess Saraswati, who is the embodiment of studies, she keeps on practicing her Veena and also reading. That shows that one has to keep on learning as much as possible. And also, if you are a practicing musician or practicing something, not necessarily music, anything, you have to keep on the practice. And that is what she does by playing on the veena. So my sincere advice to your young people is that you try to learn as much as possible and never stop learning, never stop updating your knowledge. And also practice whatever. And don't ever think that something is unimportant or unnecessary. Let me also tell you that sort of an idea that something is not important, I don't have to learn this idea comes only from the lower 25% of the class. The upper 50% never say that. They never think something is unimportant. The lower 25 people will only feel because they are not able to score good marks. Okay. So that's what I have found in all these years of experience. So when such a thought comes to your mind, ask yourself, am I in the lower 25% of the class? I should try to move. I should never think something is unimportant and try to learn as much as possible. So with this advice, whether you like it or not, I will stop.
It's
and
like
thanks for this invitation. I appreciate it.
Okay, thank you, ma'am. Thank you so much for sharing your knowledge with us. Now, I would like to invite Dr. Rekha Jain, HOD Mathematics, for the words of acknowledgement. Please, ma'am.
Thank you, Megha. It's an honor to have been asked to offer a vote of thanks on the occasion of expert lecture. On behalf of Medicaps University, I extend my gratitude to our today's expert, Dr. Kamala ma'am, Ma'am, thank you so much for your valuable time and your advice. Ma'am, we promise you that we will keep on updating ourselves, and your words will keep on motivating that we should not stop practicing. So we'll do it, ma'am. Thank you so much. It's an honor and privilege for us to have you. Thank you so much. I would like to extend gratitude to our Honorable Vice Chancellor, Dr. S.K. Somani sir, for sparing his valuable time. His kind suggestion and motivation are always inspire us to do such program. Thank you so much, sir. I am thankful to our respected Dean, Dr. Preeti Jain ma'am, for her continuous motivation and support. I would like to thank convener of this program, Dr. Rinku Verma. Because of her efforts, this lecture took place. Thank you, Rinku. I would also extend thanks to all faculty members of the mathematics department for their support. I would like to thank our registrar, Dr. Yadav, for all his backup support. Thank you, sir. A big thanks to our technical team, Mr. Surikant Soni and Ms. Amrita Mantri, for all technical support for smooth conduction of this online lecture. Last but not the least, thank you all participants for attending this lecture. Thank you so much. It's a great pleasure to having all of you in this online lecture. Thank you so much. Thank you, ma'am.